When you hear the term oil sands, most people picture huge mining operations, which have a massive footprint, moving millions of tons of ore and overburden every single day. While mining has been around for almost 60 years, it only accounts for about half of all oil production from the oil sands. The other half is extracted deep underground with very little land disturbance, much like conventional oil. This process is referred to as thermal in-situ extraction. Thermal because steam is used to mobilize the oil, and in situ meaning the oil is recovered in place, leaving all the sand behind. There are over 24 commercial thermal in-situ facilities currently operating in the oil sands, mostly located on Alberta's eastern edge, stretching from just south of the Cold Lake area to as far north as Fort McKay. The two oldest facilities began commercial operations in the Cold Lake region in the mid-1980s. The Cold Lake facility operated by Imperial Oil, and Wolf Lake, originally developed by BP and now operated by Canadian Natural Resources. Both facilities extract oil from the Clearwater formation, located about 500 meters below the ground. Clearwater is a relatively tight sandstone formation with very low vertical permeability, meaning it has very poor vertical flow properties. Cold Lake and Wolf Lake use a process known as Cyclic steam stimulation, or CSS, which leverages relatively high steam pressures to improve reservoir permeability, typically very close to or slightly above the reservoir fracture pressure. Cyclic steam stimulation is carried out through a single well, which alternates between three distinct phases: steaming, soaking, and production. With each cycle, oil is removed and reservoir permeability is improved, allowing for a subsequent reduction in pressure. As you move north into the Athabasca region, most recoverable barrels are contained within the McMurray formation, which can be anywhere from 100 to 500 meters below grade. McMurray is a much looser, unconsolidated sandstone with a very high vertical permeability, meaning the reservoir has very good vertical flow properties. Facilities operating in this region use a process known as steam-assisted gravity drainage, or SAGD, which operates at much lower pressures than CSS. In this case, a pair of horizontal wells are drilled into the pay zone, stacked perfectly above each other. The production well is located about 2 meters above the bottom of the pay zone. The steam injection well is drilled 5 meters above it. SAGD is a continuous process. Steam is continuously injected into the top well, mobilizing the bitumen and pushing it towards the outer edge of the steam chamber, allowing it to gravity flow to the lower production well. While CSS production has been little changed since the late 1990s, SAGD output has grown by over 1 million barrels per day in the same time frame, making it the fastest growing segment of the oil sands. SAGD production is a lot more efficient than CSS, using less steam to get more oil out of the ground. This step change in efficiency can be attributed to 6 key technological innovations that all happen below the surface. 1. Improvements in geophysical modeling and resource delineation, giving operators a much better idea of exactly what's buried underground, helping them more accurately model drainage patterns over the entire lease. 2. Greater precision in horizontal directional drilling technology, allowing operators to optimize resource recovery while steering clear of pesky thief zones that suck up steam and block heat transmission. Three, improvements in seismic data acquisition, which is kind of like doing a CAT scan on the reservoir, giving the operator a very accurate picture of what's happening underground, not just during the initial planning phase, but through the entire life of the facility. Number 4, industry-wide adoption of enhanced recovery methods, like infill wells, the addition of solvent along with the steam, and co-injection of a non-condensable gas, extending the production life of each well while using less steam. Number 5 is the use of flow control devices, which are used to improve steam chamber conformance. Outflow control devices help even out steam distribution, and inflow control devices even out oil drainage rates along the entire length of the well. This improves steam chamber conformance, which improves reliability and overall steam usage efficiency. And finally, number 6, advancements in mechanical lift technology, specifically electric submersible pumps. ESPs can handle high emulsion volumes at bottom hole temperatures in excess of 250 degrees Celsius. This has allowed operators to lower the steam chamber pressure, which improves steaming efficiency and reduces interference with thief zones. These subsurface advancements have helped propel Alberta's total in-situ production to almost 1.8 million barrels per day by the end of 2024, putting in-situ production on par with total output from oil sands mining operations. If you're interested in learning more about thermal in-situ production from the oil sands, I invite you to check out our latest course, Subsurface Planning and Operations. We'll explore everything that happens below the surface in a typical thermal in-situ facility. Check out the links below for more information. Thanks for watching and hope to see you in the next video. Bye for now.